Hello and welcome to Bio40 Pre-Lecture 31. This time we violate more of the Hardy-Weinberg assumptions. We mentioned last time how violations of the Hardy-Weinberg assumptions lead to changes in allele frequency, which we call microevolution. We've covered selection. Now let's see what the consequences of small populations are. The genotype frequencies we calculate with Hardy-Weinberg would only be exact with infinite populations. A real population, with a finite number of individuals, is bound to deviate from those frequencies. We call this genetic drift. And the smaller the population, the larger these fluctuations can be. Just like when you flip a balanced coin, you expect the frequency of getting tails to be 0.5. But if you only flip the coin 4 times, it shouldn't be too shocking to get a frequency of 0.25 or 0.75, or even 0 or 1. Suppose we start with an initial population of 2. One individual is homozygous dominant, and the other is heterozygous. So the initial allele frequencies are p equals 0.75 and q equals 0.25. Now suppose the population of the next generation is also 2. What are the odds that the recessive allele is completely lost in the next generation? Well, there's a 50% chance that any given child doesn't get a recessive allele. So there's a 25% chance that neither child gets a recessive allele, and q becomes 0. Though it's equally likely that both children get a recessive allele, and q increases to 0.5. Here's another example of how large the fluctuations can be. Imagine a population of 10 individuals that starts with initial allele frequencies of both p and q equaling 0.5. Then we simulate how the allele frequencies will change over 30 generations if the population size stays the same. There's no selection here. The fluctuations are solely due to drift. If you repeat the simulation 6 times, you can see 6 very different results, all because of random chance. Sometimes the recessive allele is lost, and the dominant allele is the only one remaining. In such cases, we say the recessive allele is extinct and the dominant allele is fixed. Other times, it's the dominant allele that becomes extinct and the recessive one that's fixed. And sometimes both alleles persist for the entirety of the simulation. With larger populations, you see much less drift. This population of 500, over the same number of generations, displays much less variation from the initial allele frequencies of 0.5. The same way that when you flip a balanced coin 500 times, you don't expect the frequency of tails to be very far from 50%. So that's genetic drift. Now let's take a look at the effect of mutations. Mutations are the ultimate source of genetic variation. There would not be dominant and recessive alleles in the first place if it were not for mutations. A mutant allele can be dominant or recessive to the wild type, but it's more common for the mutated allele to be recessive. However, even this mutation rate is pretty low. When we first discussed mutations, we said the rate in mammals is 10 to the minus 4th to 10 to the minus 6th per gene per generation. With a little over 20,000 genes, this means on average, a given human gamete should have between 0.02 and 2 mutations. But by itself, this would make for a weak evolutionary force. The recessive allele frequency would only increase by about 1 times 10 to the minus 5th per generation. But the combination of mutation and selection can be quite powerful. We said before that mutations can be good, bad, or neutral. Let's imagine a mutation of allele A to A prime. We'll use A prime because the following rules don't require the mutation to be recessive. If the mutation is neutral, as most mutations are, there will be no difference in fitness and therefore no selective forces acting here, though allele frequencies can still change due to drift. With deleterious mutations, where homozygous mutants have lower fitness than wild type, there will be a negative selective pressure, and the allele will move toward extinction. But with a rare minority of beneficial mutations, where the mutant has higher fitness than the wild type, positive selective pressure will move the mutant allele toward fixation. Let's look closer at deleterious recessive mutations. At conception, the genotype frequency for homozygous recessive individuals is q squared. But some fraction of those individuals will not survive to become part of the mating population. This fraction is the selection coefficient S. which you'll recall is equal to 1 minus W. So SQ squared is the rate at which the recessive allele will be lost. The rate that new alleles appear is a mutation rate, for which we use the symbol mu. We just said that this was between 10 to the minus 4th to 10 to the minus 6th per gene per generation, which is about one new allele in every 10,000 to million individuals. Eventually, an equilibrium will be reached where the alleles gained through mutation equal those lost through selection. At this point, mu equals SQ squared. This allows us to estimate what the frequency of recessive lethal alleles should be. If mu is between 10 to the minus 4th and 10 to the minus 6th, SQ squared will have the same value. And for a recessive lethal allele, the selection coefficient is 1, so mu equals Q squared. This means Q should be between 10 to the minus 2 and 10 to the minus 3. When Q is so low, P is pretty close to 1, so the genotype frequency of carriers, 2pq, is essentially just 2q. If observed frequencies are much higher than this, you want to start considering the possibility of heterozygote advantage. You can also use this formula to estimate mutation rates. Q squared is a frequency of homozygotes, and thus the frequency the condition appears at. If the condition occurs in 1 in a million individuals, you can tell the mutation rate is 10 to the minus 6. So mutations, selection, and genetic drift all play major roles in shaping allele frequencies over time, and therefore drive microevolution. Mutations are how new alleles arise in the first place. Most of the time, the mutation will not affect fitness. The allele frequency will only fluctuate due to drift. But when the new allele affects fitness, selection will drive the wild type and mutant alleles to a stable equilibrium. The exact nature of the equilibrium will depend on the relative fitness of individuals who are heterozygous and homozygous for the new allele. If the fitness of the homozygous mutant is lower than that of the wild type, then the allele frequency will settle at the square root of the mutation rate divided by the selection coefficient. This is just a rearrangement of the mu equals SQ squared equation. Though Q can be higher than this if the heterozygote has a higher fitness than the homozygous wild type, as we observed last lecture with heterozygote advantage. If homozygous mutant individuals have a higher fitness than homozygous wild type, then the mutant allele will move toward fixation. It will be the wild type allele whose frequency is determined by the mutation rate and selection coefficient. Though once a mutant allele becomes a predominant version, it gains the status of wild type. Okay, let's stop here for today and make this a short lecture. This leaves the effects of migration and non-random mating for next time.